this year I'm being assisted by Maria Pelusi and Elise Scott, two students at Clarkson University. We have a number of other faculty and students who participated in the past and technicians at the River Institute. And so what I'm going to do first is play a brief video. It's 3 minutes long, kind of sets the stage between wetlands and water quality. And then what I'm going to talk about are various observing systems that we find throughout the Great Lakes region. And then I'm going to focus in more on the St. Lawrence River. And then I'll talk about more specifically the approaches we've used to observing water quality in the St. Lawrence River, mostly in the summertime when we can use boats. But then also the approach that we've taken now, which is to measure water quality during the wintertime. So on a day like today, when it's pretty cold out and the river is frozen over, we have the ability to measure water quality. So here's a very brief video for you to watch.
The hydropower dam that was constructed in the late 50s on the St. Lawrence River had a very significant impact on the habitat of the river. As you can imagine, there was once a 10-mile torrent of white water and then becomes a lake. Mind you, it's what we call a fluvial lake because the water is constantly flowing through it. But nevertheless, the water levels have been maintained abnormally high over the past 60 years now. And that's had an impact on the wetlands in the area. However, the types of wetlands that developed because of the tight regulation of the water levels has been monotypic stands of things like cattails. And so in those type of wetlands, the diversity is not as high as it could be. The fish aren't able to breed inside these wetlands because the cattails are too dense. And so what they want to do is create more of a natural type of water regulation plan. It's called Plan 2014. With Plan 2014, the water levels will follow a more natural cycle. So in dry years, the water naturally will go lower. Wet years naturally go higher. And by following that, they can get back to a more natural system. So right now, there's about 30% more wetland than there should be in the St. Lawrence River. We have two experiments that we're doing right now. One experiment is a long-term data set, water quality data that are being collected on the St. Lawrence River at the Moses Saunders Power Dam. And so we have instruments that are placed inside of the power dam and measure water as it flows downstream. And by doing that, we're able to make a number of different observations. And ideally, when Plan 2014 becomes invoked, how the changes in the water level can actually affect water quality. The other experiment we're doing is measuring how much mercury and nutrients are found in the wetlands of the St. Lawrence River, because what we're concerned with is that in the future, when we start eroding the wetlands, like we want to get back to the natural type of wetlands, we want to reduce about 30% of the current amount of wetlands in the river. There is historically legacy amounts of mercury, phosphorus, and sulfur in these wetlands. And so when we erode those 30% of the wetlands, that means that material, those nutrients, in the case of mercury, that contaminant, is going to get mobilized into the river. We, this summer, have determined how much mercury will come out, and we need to keep in mind that that mercury has to go somewhere. Is it going to get in the food chain? Is it going to go downstream? We don't quite know yet. And this all comes back to the management of the river. In order to manage our water quality and aquatic habitat, we have to understand it. We understand that we need to reduce the amount of wetland that's currently in the river, bring it back to the more natural levels, which opens up the diversity of habitats. However, what we don't know is the rate at which the mercury that we now know is in those wetlands. How fast will it get in the water? If it gets in slow enough, then we can say, hey, it's not going to have much of an impact. It'll be essentially dispersed effectively. But if it comes out in large amounts, it can affect the amount of mercury found in the fish, more so than right now. And so we can protect humans by saying we're going to have new fish advisories for the St. Lawrence for a certain amount of time while this mercury gets eroded out of the system. But there's other animals like mink, osprey, eagles, which really don't follow fish advisories.
All right, and so that was just a brief description of the impact that the Moses Saunders Power Dam had on the river. And so there are ramifications of having a dam on a large river like the St. Lawrence. And so what we do need to do, though, is make observations of water quality so we can determine, what is the impact that's had and how can it change with our own changing relationship with the land. And so one of the things that, one of the reasons why we want to measure water quality and have sensors is to do things like, determine what the impact of road salt is in the region on our water quality. Also, to look at harmful algal blooms, things like microcystis, which I'll talk about more in a moment. These are cyanobacteria that, if they proliferate, means that we either have to shut off our water source or we have to get our water source from somewhere else. And then we have climate change. And I spoke briefly about changing water levels and the impact that it has on biodiversity, but also has an impact on things like infrastructure. But as lands dry and lands get inundated, it does change the water quality of the water that once flowed over near the land or no longer does. And so finally, we also have this ability that we want to be able to swim in the water, we want to be able to drink the water, and we want to be able to eat the fish from the water. And so what is this really large river that we're so intimate with in our region? In the background here, this is Lake Ontario, and this is from an airplane flying, a couple thousand feet up. So you can actually see the curvature of the earth. That's a very large lake. And what's interesting about the St. Lawrence River is that it starts as a very large river right away. It's not like, say, the St. Regis River or the Racket River, which start off as small ponds up in the Adirondacks and then get larger as they flow downstream. The St. Lawrence starts large right away. It's the largest fluvial source of water to the Atlantic Ocean. It's a multinational waters. You have Akwesasne, you have Canada, you have the United States, all sharing jurisdiction of the water. And what's interesting is that the water residence time in the entire section of the river is 12 days. So you calculate the volume divided by the flow, and that gives you 12 days. However, here's a ship that's going right down the main channel, and the rate at which the water flows down the main channel is only 5 days. So if you're sort of floating in your life jacket from Lake Ontario down the river, you'll get to the dam within 5 days. So it follows that other water bodies or bays and inlets in the river must take longer than 12 days to get downstream. And I'll talk a bit more about that, sort of the nearshore shape of the river and how it can affect water quality. And as I mentioned in the video, there's been a dam on the river since 1958, and the water levels are tightly regulated. And so this is the whole section of the river up here. So Lake Ontario, we have the Thousand Islands Archipelago in this area here. It's the single thread reach over here between near Brockville and Morrisburg, New York. And then down here, there's fluvial Lake St. Lawrence, which also has an archipelago, but it's much more shallow than the Thousand Islands region. And so some of the background for this, as I mentioned in the video, there's been an effort to bring back a more natural way of regulating the water levels, and that's called Plan 2014. And it was designed to allow higher water levels during wet years and lower during dry years, so that you will end up having a more natural type of ecosystem. Because what's happened in the past is that the cattails have grown out as far as they possibly can, and it's blocked the kind of good habitat that existed 60 years ago now. So water levels affect the nearshore. Those are the most affected by changing water levels, and nearshore has an effect on water quality. There's also the need to understand how the river is going to change with climate change. And finally, according to the Great Lakes Water Quality Agreement, each of these rivers that drain and connect the Great Lakes are now considered part of the lake-wide management plans. And in the past, they've had not the same amount of attention. So if we want to manage them or establish understanding of our relationships with them, then we need to know more about these water bodies. So here's some approaches to observing water quality. So these diagrams I have down below here are essentially maps. So if you look at each of these as a map, that's your latitude on the y-axis and longitudinal on the right. And if the river is flowing from left to right, one way of measuring the water quality would be to take a boat, like you saw in the video, and put instruments on board the boat, and then as you drive or steam along the river, you can measure water quality at various geographic locations, and that gives you some coverage. Another approach is to follow what are called transects, or longitudinal transects here. So you go along the near shore, say that's the New York side, you go up the main channel, and you go up the Canadian nearshore side. And so you're not covering as much as the in-betweens, but you can actually cover more in a day. And then finally, this last technique here is what we're doing in the dam. And so here we have sensor locations, observation points that are fixed in space. But over time, the water comes to the observation point, and you can measure the water quality over time. So a quick overview of the kinds of sensors that we have available at our disposal to use in the dam and on the boats. They're essentially electronic sensors. So we can measure temperature and what's called specific conductivity, or the amount of salts that are present in the water. We can also use various sensors that utilize light. And so fluorescence can excite a chemical using a light. And we often have the sensors use ultraviolet light, and I'll describe that in a moment. And so the kinds of things that we can measure are things like the natural pigments that we find in phytoplankton, such as chlorophyll. Phycocyanin is a specific pigment found in the cyanobacteria that cause those algae blooms. And then there's this thing called colored dissolved organic matter, and also various pollutants. And I'll focus on CDOM and the various pollutants on the next slide here. So this is colored dissolved organic matter. So if you went up to Waddington and you flew over and you look at Sucker Brook, you see it's got this brownish water color to it. And the St. Lawrence River is actually quite clear. And so it looks, in this case, it's reflecting blue, and down here, Sucker Brook is reflecting brown. And the reason why it's brown is because of the high amounts of CDOM. It has about 10 times more CDOM than the St. Lawrence River itself. And what is CDOM? CDOM is actually the degradation product of biomass. And so you've probably seen a leaf that falls in the autumn, and it lands on the sidewalk and or on a deck, a wood deck, and as it gets wet, it leaves an imprint. And so that imprint is actually organic matter that's left behind. It's like a dye or a tea. And so it really has no defined chemical structure, but we know that it's able to color the water. And because of that, we can actually trace water that has color in it. And what's nice about these sensors that we use is that they're very sensitive. Okay, so here's an approach using CDOM and temperature to characterize water quality in the St. Lawrence River using this cross transect approach. So we're steaming back and forth across the river. And so we started up over here, and this took about a day's work, and we steamed back and forth. And then in places where it's not colored right there, that's because the boat couldn't go there because it's too shallow, or there's rocks, so we avoid that. And then you'll see that what we can do is we can take our data, we can put it on the map, and then we can sort of interpolate the values as they transition from one spot to the next. So it's kind of like what they call a heat map. And so this area here that's blue colored, that's actually very cool water, and it's got very low concentrations of CDOM in it. So that's the main channel of the St. Lawrence River. It's kind of like, at this point, 4-day-old Lake Ontario water. And then there's other places where the water is warmer, and there's also low CDOM. So that's an area where the river water from the main channel has curled in behind, and it stays in a shallow area and warms up. And then we have these other areas here with high CDOM, but also high temperature, and those are areas that are affected by nearshore tributaries, so Howassick Creek and Brandy Brook. So this is kind of a nice interesting snapshot, but it's just one day's work. And so having a long-term data set over the course of years would be a tremendous amount of work. Plus you'd have to have as many boats to cover the entire river. So it's kind of a challenge. The other way that we can cover more ground is to use a boat where we can steam up and down, steam up upstream. And so right here, I'm showing you Lake St. Lawrence. This is over here. This is the power dam on the far right where we start. And what we do is we follow the nearshore. And so we steamed up along the water where, steamed up along the shoreline of the river where it's only 2 meters deep. And we did that on the Canadian shore, like that. And then we did it on the US shore, go around the corners here. And then we also went up the very middle. Now the data, the colors that you see right there, the red, the green, and the blue, those are based on some modeling applications that I'll talk about later. It just kind of shows the different water masses. Over here in these panels on the left-hand side, these are the actual observations we made as we were moving upstream. And so if you look at the green here, as we go from the dam upstream over the course of the day, the water actually cools off slightly. And that's because water flows into Lake St. Lawrence and stays there and starts to warm up. And we're going the opposite direction. So each of these lines took a day, as you can see down below here. And so if we go up the New York shoreline, and we start over here down by the dam, and we tootle along this way, and we go up all the way up to the Iroquois Dam, what we'll see is these peaks of the temperature is higher, and this down here is the amount of chlorophyll A, and we also see that if we go on the Canadian shore. So what we're showing there is that as we get into these areas where there's little bays, the temperature increases quite a bit. And you probably know that if you swam in the river, you know that some bays are warmer than the main channel. But also what's interesting is down here in the bottom panel, this is the amount of algae. You can see the amount of algae in the main channel is quite low, but near shore, there's a lot more algae. And so there's different areas, little nooks and crannies, so to speak, in the river that support different communities that are present in the water column. Okay, so now we get to the last sort of method that we've chosen. This is what we've been trying to show, that this is likely the best way to do our kind of measurements. And it's using the fixed locations. And so this is upstream of the river, of the dam. And here's the dam from shore to shore. And there's 32 turbines across the dam. And we have put sensors in unit 32, 17, and unit 1. So we've been in unit 32 since 2014. So we're into our 7th year of observations, although last year, as you can imagine, has been quite a challenge. And so where are these located in the dam? This is a cross-section of the dam itself. And so here's the head pond, and the water flows down through the penstock, goes through the scroll case, turns the turbine and out through the tail race, and generates electricity. Up here, this is the stator, which generates the electricity. It gets warm because it's heavy and it spins, and so there's friction. And the folks in the power dam use the water from the penstock, and they run it through these excuse me, radiators in order to cool off the stators. And so what we do is we tap into that water before it gets to the stator. And so the water comes through quite quickly, and it's all mixed up, but it's mixed up along the shore here, or in the middle, or on the other shore. And this mixing is kind of like what you see in this picture right here that I talked about earlier, the hydrodynamic modeling. And so my colleague, Joe Skufka, in the mathematics department, he has the bathymetry of the upper St. Lawrence River. And if we know the water heights and the bathymetry, then you can actually predict where water will go. And so he can actually do that in reverse as well. So he can put colored balls, so to speak, in the dam like this, or in the middle, or in the near shore side, the different units that we've got our sensors in, and it can sort of say, where did that water come from in the previous, say, 3 days before it went through that unit of that turbine in the dam. And you can see here that in unit 1, this water had these kinds of origins 3 days prior. Unit 17 had origins like this, and unit 32 had origins along this range here. And so there's very little overlap between the two. The blue and the red do not touch one another. The green barely touches the red, and the green kind of comes near the blue, but for the most part it does not because it's traveling so rapidly. So these are what the instruments look like inside the Moses Saunders Dam. Here's the 1 foot diameter pipe that comes out for the cooling, and you can't see it, but down over here there's a tap which we've got stainless steel piping for. The water comes up here, goes into our unit called the C6, which has all these sensors over here in it, and then the water flows up and then it goes through the conductivity sensor, which is called our YSI. So also measures temperature, and then the water flows down the other way. We collect all our data on this computer, and I'm not showing it, but we've also got nice pipe insulation on all these pipes, so the water doesn't change in temperature as it flows through. It goes through very fast, but we put the insulation on anyway. And we're able to collect data every 1 to 3 minutes. So over 6 years, we have lots of data. One thing that happens every week to 3 weeks is we go in and we take apart our instruments and we wash them up to make sure they're running properly. We unload the data. We also take some water samples to measure various nutrients and the types of phytoplankton and the sizes of those phytoplankton. And we're also measuring mercury because, as I mentioned in the video, we're very interested in how changing water levels can change mercury concentrations. Here are some data. And so here is a picture on the right-hand side of Lake Ontario, the St. Lawrence River. Here's the dam. And up at Ogdensburg, there's the river that passes through is called the Oswegatchie, and that flows from the Adirondacks. And so this is interesting. It's 70 kilometers away from the dam, and I can tell you that we can detect what's happening in the Oswegatchie River if we're at the dam. And we can do that, I'd argue, any day of the year. So normally you would have to go up to the Oswegatchie and go to the dam to make measurements, but here we could just stay in the dam and make measurements of what's happening in the Oswegatchie River upstream. So how does this work? Well, let's look at some things like water discharge. And so that's the blue, that's the St. Lawrence River discharge. You can see annually it increases in the summertime. And then up here, this is the flood year, 2017. The flow is, almost over 10,000 cubic meters per second. And the brown color here is the CDOM. And you can see that the CDOM flow and that of the discharge of the river, or the concentration of CDOM and the discharge in the river, don't quite match one another, which is interesting. And so this is on the unit 32, which is right near the shore on the US side. But if we take these same data up here that we plotted, the CDOM data, and we superimpose it with the discharge of the Oswegatchie River, all of a sudden we see a very nice correlation between increase in discharge in the Oswegatchie River and increase in the amount of CDOM. And that's because the Oswegatchie River has a high concentration of CDOM. And what's happening is that when it flows into the St. Lawrence River, it doesn't dilute fully. You saw that in the earlier picture, or the hydrodynamic modeling photo, graph rather, that shows that the water that's blue sort of hugs along the shore, doesn't mix all the way across. And so in other words, when the Oswegatchie River flows into the St. Lawrence River, it actually stays along the shoreline, and then when it passes through the dam, we can detect the CDOM that was discharged into the river at Ogdensburg. Another example of this is the freshet. So this happens close to now, where the snowpack in the mountains starts to thaw, and the water flows down into the Oswegatchie River and the Raki River and all the rivers that drain the Adirondacks, and they swell up the water into the St. Lawrence River. And so what's happening here is just this. We start off with water that's very cold. This is the red. So this is the St. Lawrence River at unit 32, and we're about 0.1 degrees Celsius in mid-March. And what happens is the water starts to warm up as the days are getting longer, and that warmer water is coming in. And what's also happening here, this is the discharge in the Oswegatchie River. that we're following, it's increasing, and so too is the CDOM. And so that's, again, that nice tracer that the CDOM that we're seeing at Unit 32 is due to the discharge of the Akwesasne River. And the other thing that supports that is this right here. These black values here, that's the specific conductivity. And so that's showing that the water that's coming in and being measured in the St. Lawrence River at Unit 32 on the New York side of the dam is becoming less salty. And that's because the Akwesasne River and all that snow is not salty. It's up in the mountains, okay? So it's not, we're not talking road salt problems here, but snow is more close to distilled water than is, say, water in the St. Lawrence River. And so there's a nice correlation between a decrease in conductivity and an increase in the discharge and increase in CDOM. We all experienced the high waters in 2017 and years after. And so the reason for that was they had to hold water back to prevent flooding downstream. At the same time, there's a lot of water coming through the system, had to go somewhere. It ended up spilling onto the shorelines. And so you can see here in 2017, there's some of the highest water levels detected. Excuse me for a second. There we go. All right. So what kind of impact does that have on water quality? Well, here we see water quality. We're looking at chloride and sulfate. These are ions that we find naturally in water. And then when the discharge came, it became quite apparent that in 2017, there's much higher concentrations of chloride for some reason prior to the year. You can see right there. Before, the chloride and sulfate were in similar values, but then there's this disjunct the year before. Can we use that as a predictor of what can happen in the future? If chloride goes up, then we know, hey, there might be more flooding occurring the next year. Right now, I can't think of any connection between the two other than the fact that this looks like it was a precursor of those conditions. And what also happened was when we had that high amounts of flooding, these solutions this concentration of these salts went down quite low. That's because they're being diluted. We can measure phosphorus export from in the river. And so you can see here there's an annual cycle of phosphorus. It's very low in the winter time and it increases in the summer because in the summertime you get more mobilization of phosphorus on the lands. And so this is quite useful because we can measure the amount of phosphorus coming into Lake Ontario and the amount of phosphorus going out of Lake Ontario. And these data that we have right here kind of support that. So we can use it to understand our relationship with Lake Ontario when nutrients get into it, how much are actually going to leave the system. And so it helps with those folks who are involved with wastewater treatment. This is the nitrogen to phosphorus ratio, and if you're not familiar with this, you'll have to take my limnology course at Clarkson. We can talk at length about it. But suffice it to say, what happened with the flooding is that it disturbed the nitrogen phosphorus ratio. So there ended up being a lot more nitrogen in the water than there was phosphorus. And why is that important? Well, nitrogen, as it turns out, is very supportive of cyanobacteria. So here are some students on the river, and we've collected cyanobacteria. And these are the cyanobacteria concentrations each summer. There's a bit of a peak, okay, like this. Sometimes in the wintertime we get these peaks, and as I was explaining to students this morning, I think it's due to winter storms, which can stir up and bash up the rocks along the shoreline, and can release some algae that have attached to the rocks. But what we saw here, a year after the flooding in 2017, here's the flooding 2017 to 2018, the peak wasn't high, but the following year, it was very high. Remember, the following year after the flood, there was a high amount of nitrogen, so we think they might be connected. The other thing to bear in mind is that 2018 was the warmest year on record, and we've got this high water temperature here. Cyanobacteria like warm temperatures. Okay, so one of the next things we're going to be doing in collaboration with the River Institute is installing a couple new sensors on board the sensor arrays. And one is called an optical brightener, and the other one is tryptophan. So this is the amino acid tryptophan, and tryptophan is found in protein, and it breaks down in protein, and we eat protein, and so it gets in our sewage. Optical brighteners are things that are agents that are added to some clothing fabrics in order to make the colors look brighter than normal. And what happens is they dissolve into the wash water, and they go into the sewage. And so if you see optical brighteners and you see tryptophan together, then you can say, ah, that's an indicator of sewage. If you see just tryptophan, that would mean that, oh, there's probably some kind of manure that's happening, but it's not coming from human sewage because you'd likely have optical brighteners in there as well. So they're kind of like tracers. This is work done by the River Institute on the Canadian shore. You see they've got some very similar instruments that we use in the Moses Saunders Dam. Here's their C6, and they're pumping water out of the river through the instruments as they go along their transect. Then they make their measurements using the GPS. So there you have it, and periodically they'll take a water sample for confirmation. And this is Cornwall, and this is Cornwall Island over here, and this is the northern channel. And so here, these are the brightener concentrations that are high out here in Gray's Creek Marina area, and then get reduced as you get into the main water body. And so why they're high out here, I'm not that familiar with the region. I don't know if there's some septics that might be leaking into there. There might be some combined sewer overflow. I'm not sure, but it was detected. And there's tryptophan also being detected. So if there's optical brighteners and there's tryptophan, I would say there's some kind of huge sewage signal that's happening in Grays Creek Marina. And so now what we need to do is go in and find out where's it coming from. This is at Long Sault Marina, and this is the wastewater treatment plant, and that's the outflow, which is the red dot. So here we know we have a sewage input. And what's happening here is that you expect the sewage to go right out and dilute into the main channel, so it's low concentrations here. So here they're doing a transverse section. And so it's high around here, but it's also high sort of to the west. So it's interesting that there must be water circulation that's occurring, which is not allowing this material to fully dilute out into the main channel. So what are some of the issues that we have with the operation? You saw in those data earlier that periodically there's some chunks missing from the data. That happens for a number of reasons. One, which you might find it's kind of ironic, is periodically there's power outages of the 120 volt power that supply our instruments in the dam. Also, there are some maintenance issues. Periodically, they need to replace transformers and things like that. And one time it shut down for 3 to 4 months. There's also cybersecurity constraints. We cannot look at our data all the time, so we can't follow the instruments and say, "Oh, there's a break in the data stream. We must stop it and then restart it again." And so we can't use their infrastructure in the dam for that purpose. And so the best reason for that would be to know if our instruments are shut down, and then we can go to the dam and fix them. But I don't think we really need to know minute by minute what the temperature of the river is, for example. Okay, so instrument maintenance, they are quite reliable. Some of the sensors are not as optimal as we wish, and so we're doing a lot of testing to find which ones are best. And finally, there's data management and communication. As I mentioned before, with a lot of data, it's a lot of work to keep track of it. This is work by Cassie Labrazzo, who's a mathematics student at Clarkson University. And we had this problem that what would happen is when they shut down the water flow to do some work, what happens is the water sits inside the sensors and the water temperature increases quite a bit. This is 32 degrees. It's like 80 some degrees. And then it turns on again and keeps on collecting data. And so how do we detect that short blip over the course of weeks? Well, we can see when water shuts off, water turns back on. So we want to be collecting data back on here. From there to there is where we want to get the data for. We want to chop out the section in the middle. And so what Cassie did is she invented a way of calculating when water turned on and when it would come back on, by knowing the change in the temperature, and then she'd work backward to see when did it get closest to the temperature that it was just a few hours beforehand, because the river doesn't change in temperature that much. You can figure out when water's shut off and turned back on, and then with an automated way, clean up the data. So that helps a lot. And so we're at a situation here where we are trying to prove to the various funding agencies and the state and provincial agencies that what we're doing in the dam is valuable for understanding. And so at present, we're doing this area, this approach, we're collecting data, where we're working with it, say in Excel sheets, and we're writing a publication. But what happens, and increasingly more so now, is that we've got very large data sets. And so it takes more than just a person looking at the data and saying, oh, that's an interesting observation, I'm going to publish that. Instead, we have to do this automated data cleaning and validation. And so that's where we need to have coding. And so if students are out there like coding, you'll find a very happy person in myself to speak to you about ways to help us with that kind of information analysis. And so we're still publishing papers, but there's all these other products. It's not just the paper, but it's also the code that people can use elsewhere, and also the data can be shared. So in summary, we've got these three different approaches. And if we look at the different techniques, the crossing the river, taking the transects upstream, or just fixed in one spot, we have various abilities to make measurements over the course of the summer. The dam here has the highest ability to make measurements, for example, in the wintertime. The other methods are only good when there's no ice on the river, and we know there's ice periodically on the river. What's our spatial resolution? It's kind of medium. We can go up to 70 kilometers upstream, as I showed you with the Oswegatchie River. That's interesting. Temporally, we can be there. We can make measurements every day of the year. But with these other methods, they're not quite as good, but they've got much greater spatial resolution because you can be right at that spot in the river where the water quality is. In the dam, kind of estimating what it is upstream. To make these other measurements using A and B, it takes days and multiple days if you want to do the entire river. With the dam, you kind of fixed in one spot, but it does take hours relative to days. And it's relatively low cost because we don't need a boat. And our instruments are very well protected, so they tend to last longer. So in summary, we can make these inferences about environmental quality in the river. We can start making year-long observations about the river, and this is helping us understanding our relationship with the river and how the river may change in the future with changes in the water level regulation plan that was designed to restore wetlands in the St. Lawrence River. And so with that, I'll just leave it there, and if anyone has any questions, I'd be happy to entertain any. As we look at this picture by Stephanie Hildebrand. Thank you.
Hi, I don't have a question, but I just want to say you have a really good presentation and you covered a lot. Thank you for
you're welcome,
presenting.
Megan. You're welcome. All right. So I see Elise Scott is here. She's one of the students at Clarkson who's helping out. And the other student is Maria Pelusi, and she had a job interview that started at 4:30, so she had to leave early. So that's it for now. I do know that the Mohawk Council of Akwesasne is interested in using a similar technology, and so we are going to be writing some grants together to use the water inflow, for example, at the water intakes, because there are 3 intakes in Akwesasne where they get water from the river, and using the similar kind of instruments, you could sort of monitor the water quality in the river as it's brought in for treatment for drinking and distribution. So I'm looking forward to that.
That sounds very exciting, and I look forward to those discussions as well.
Yeah, okay.
Well, thank you so much for joining us. So we're going to be reconvening, tomorrow at 11 a.m. with the Cooper Marsh Conservators for All About Cooper Marsh. And thank you so much for joining us.
You're welcome. Have a good day, everyone.
Take care.
Goodbye.
Thank you. Take care.